Hey, good morning, everyone. I'm just gonna pause for a few seconds to let people get into the webinar, as we can see people still logging in and joining, and then we'll get started. Okay. All right. Hello, everyone. I am Renee Yager. I'm the Director of Marketing at EPC, and welcome to today's webinar, GaN Device Reliability. This is the second of our four-part summer series, which is running bi-weekly through the beginning of September. Just a reminder that recordings will be available after every webinar, so you can register even if you're unable to be with us live. The full schedule and details are available on the website at epc-co.com. So before we get started, just a few housekeeping items. You will have the opportunity to submit text questions to our panel by typing the questions into the Q&A function that's at the bottom of your screen. You can send those in at any time during the presentation. We'll collect them and address them during the Q&A session at the end of today's presentation. So now I would like to introduce our speaker today. Alex Lito is CEO and co-founder of EPC. Prior to founding EPC, Alex was CEO of International Rectifier. A co-inventor of the HEXFET power MOSFET, Alex holds many patents in power semiconductor technology and has authored numerous publications on related subjects, including co-authoring the first textbook on GaN transistors for efficient power conversion. Alex, thanks you for joining us today.
Thanks a lot, Renee. It's, one of my favorite subjects here is device reliability. So today I'm going to talk a lot about that and give you an understanding of why we do this test-to-fail methodology, how our devices are characterized so that we understand how they would work in any mission. So first of all, just background. We've had parts out for 13 years now in the field. We track them very carefully, particularly in automotive and telecom applications, because those are areas where the customer is very precise about tracking every device. We've tracked over 400 billion operating hours in the field. We've had only 3 device failures to date. Those were several years ago, and since then we've improved our devices. But this is 2 orders of magnitude better than any failure rate experienced in power MOSFETs. So you can get a lot more information by going to our website. I'm showing you just the cover of our ebook on reliability. We also have it every year. We publish a new update to our reliability reports. We're in the phase 14 report now, and in December we'll have a phase 15 report. So just go to our website, look for the reliability icons, click on that, and you'll get the latest information. Now, EPC for several years, and actually going back into the late 70s when we were working on the early MOSFETs, we've been doing a test-to-fail methodology. Now, most customers and most people who make devices, they do a test-to-qualify methodology. That means they take a bunch of devices, they put them on a burn-in rack under certain conditions. They typically burn in, 77 pieces for 1,000 hours, and if none fail, it's a success. And that there are many fallacies to that. First of all, you're only testing one data point. So what happens if you use a different data point, a different temperature, a different voltage, or a different current? Would you still have a successful launch of your product and successful reliability of your product? And that kind of questioning is important. There's only one way to understand the real operation and reliability and robustness of a device under an arbitrary set of conditions, and that's to understand exactly why it fails and to understand the physics behind that mechanism of failure. So in order to do that, EPC created this table to begin with, and on the left-hand column, these are stressors. These are all the ways that you can stress a device. So for example, let's see here. I'm not sure why it's not advanced. There we go. So you can stress a device with voltage, you can stress it with current. GaN devices are faster than any power semiconductor in history, so you can also create new stresses, like very high rates of change of voltage and current. Of course, you can stress it with temperature, chemistry, like humidity or other chemicals, mechanical strains, and even radiation. And you can have combinations of these, of course. So with that, you then stress these devices under various conditions, and you create a basket of failures, a big basket of failures, hopefully, and you've characterized and you've failed them in such a way that you can now characterize why they failed. By the way, that can be tricky because often a failed device destroys its own evidence. So we had to create various technologies to fail devices and fail it in such a way that the evidence stayed there for the failure mechanism that initiated the failure. And you can see here all the intrinsic failure mechanisms that we found from all the different stress conditions. In some cases, there are unknown mechanisms or we found no mechanism. Now, today we're going to focus on two of the most common stressors, voltage and current. They come in various forms. You can stress the gate and the source. You can stress the drain and the source. You can put a lot of current through a device. You can put current and voltage through a device. We'll look at those conditions. And we'll also look at a very real world situation of a synchronous rectifier and how all these conditions can be understood in terms of emission profile and the impact it has on a device. So to get started, let's look at a device. This is a GaN transistor. It's deceptively simple. There is a source and a drain. There's gallium nitride. It's grown on top of silicon. And on top of the gallium nitride, you put a very thin layer of aluminum gallium nitride that strains the surface of the GaN crystal. That strain, since GaN is piezoelectric, generates a very high electric field, which attracts electrons. Those electrons come up to the surface, if you will, or the interface between the outGaN and the GaN, and they create a two-dimensional electron gas. You can see little dashes there. That two-dimensional electron gas is under such an enormous electric field that it actually has quantum mechanical properties, which means that you can get very high electron mobility and very high saturation velocities. The electrons are very slippery in there, much, much more mobile than in silicon. On top of that, you protect it with a dielectric, you add metal field plates, and that's kind of how you make a device. Now, this is what it looks like in real life. So here I'm pointing to the source, the gate, the drain over on the right. You can see the GaN that's grown on top of silicon. Silicon's at the bottom. Also, there's a metal field plate, which was gray in the prior image. You can see that. Now, their sources are back to back. Let's magnify a section of that. So I'm taking that one little piece there. We'll use this cross-section in a few other places. So let's take a look at it. You can see that the GaN is basically at the bottom. Then there's a pGaN gate. That's magnesium-doped gallium nitride, which acts as a semi-insulating gate with acceptor-type properties, which gives you an enhanced mode device. On top of that, you have a metal, gate metal. It's tinitride in our case. And then it's separated from the source metal and the source metal field plate with that dark strip, which is silicon nitride. Okay, so that's the basic structure of a GaN device in real life. These are all sub-micron elements. The gate length, that would be the lateral distance of the pGaN gate, is about a half micron. So let's stress this device. We're going to first stress it gate to source. What we did was we took thousands of devices and we stressed them at various voltages. We started at about 8.5 volts because we couldn't create failures in any reasonable amount of time before that. We got to 9, 9.5, 10, 10.5, things like that. And you generate a bunch of failures. And this is not just an example. This is an example of thousands of failures. The failures preferentially occur in this location. Now you can see the GaN at the bottom. You can see the gate metal and the dielectric. And then the metal one field plate, and then there's that big burn mark, and it's between the gate metal, which is tinitride, and the aluminum field plate. In other words, it popped through the silicon nitride. And this is what happens with all the gate failures when you apply a voltage for a long period of time. So this led us to developing a physics-based theory on why that happens. Now, one of the mysteries was, well, we can see failures at 8.5, 9 volts, and there's about 1,000 angstroms of silicon nitride. Well, that's too low of a voltage for silicon nitride. So why is that gate failing well above our 6-volt maximum on our gate on our data sheet, but well below the theoretical limits of silicon nitride? And that led us to an understanding of the impact ionization mechanism that triggers time-dependent dielectric breakdown in the silicon nitride. And let me explain it to you here. So here you have a cartoon showing the cross-section. At the bottom is the gallium nitride. You can see the two-dimensional electron gas. You can see the alGaN barrier that creates the strain that generates the two-dimensional electron gas. Above it is the pGaN. Now, electrons, when you have bias on the gate, electrons in the 2-deg can actually get accelerated in that electric field to the point where they can actually hop over the alGaN barrier. And you can see that happening right there. They have enough energy to jump that barrier. Now, it occurs well beyond our data sheet, but this becomes the intrinsic failure mechanism. Then they go zooming up that pGaN as they're accelerated in that electric field, and they might hit something, a lattice imperfection, whatever, and that's impact ionization. And it generates holes, and the electron gets deflected off. The hole can be bounced into the silicon nitride right there. And that then creates a small pocket of high concentration of charge, which is a little bit like a plasma torch. Some of the purists don't like my analogy, but it's like a plasma torch drilling through that silicon nitride, and eventually you generate a dielectric gate rupture. So two mechanisms: time-dependent dielectric breakdown, accelerated by impact ionization. Now, this can be characterized very well using well-understood physical principles. I won't go through these calculations, but these calculations basically show the rate at which impact ionization should lead to a time-dependent dielectric failure. In this case, we've calculated in terms of mean time to failure. We can calculate in terms of any kind of failure rates. I'll show you that in a minute. But what's important is that this mechanism is not a curve fit to our data. In fact, it's using our models use peer-reviewed literature. In particular, the work of OIE here was used to generate the key coefficients of A sub n and its impact with temperature, which you can see in the lower equation, and as well in B sub n there as well. So these things are not, EPC generating a bunch of failures and then using a polynomial fit to figure out failure rates. It's actually using the basic physics of the impact ionization and time-dependent dielectric breakdown. This is the resulting final equation in terms of, again, variables that are available from the literature. We've simplified some of those variables. In our reliability report, you'll see the simplifications that we've used. In other words, we've combined several variables into A and B in this equation, as opposed to just calling them all out. Those are the values that we used in A and B, and let's see what it showed. So we're going to look at theory versus experimental results. We use the equation I just showed you and the values that I showed you as well on the prior page, and here you go. On the vertical axis, you have time to failure. On the horizontal axis, you have gate voltage. I drew a vertical line showing the maximum gate voltage in our data sheet, 6 volts. And you can see the various lines are not straight lines. Straight diagonal lines would be consistent with time-dependent dielectric breakdown in a planar insulator. But this is not a planar insulator. It has that accelerant of impact ionization, and that generates that curvature. In fact, it asymptotically curves to the theoretical dielectric strength of silicon nitride. But as you get to higher and higher gate voltages, the impact ionization accelerates it more and more, and that's why you get the curvature. And you'll see the actual data points from our failures and the error bars in those data points that confirm that mean time to failure line. Now, as I said, all these numbers are well beyond our data sheet. In fact, that 10-year line is the dotted horizontal line that you see there, and you can see that the 1 ppm line crosses the maximum rating and the 10-year line. So we should see less than 1 ppm failure rate from our devices. In fact, we have never, ever had a field failure from a gate in our devices. Now, what about temperature? One of the things that we observed very early on from the thousands of devices that we failed at various voltages and temperatures was there was a negative temperature coefficient. What that means is that the higher the temperature you go, the more reliable the gates were. It's a continuing theme with gallium nitride, and one that is counterintuitive to most people that have worked in the world of reliability of semiconductors. But here it shows you there is a mild negative temperature coefficient in terms of gate failure. And I'm showing the mean time to failure on the vertical axis. On the horizontal axis, again, gate voltage, same scale as the one on the left. But in this case, the three lines represent minus 75 degrees C on the green, 25 C or room temperature, the blue, where you see the data points, and then the red is 125 C. And we have data points on all those lines. We just don't show them here. So what's the big takeaway? Gates are very reliable. If you don't go above 6 volts, you'll never see a gate failure. What's the other takeaway is even as you go to higher temperatures, they get even more reliable. Okay, so let's stress something else. Let's go to drain source voltage. And this is a trickier one because there's a lot more, I'll say both history of this and a lot more mythology behind drain source voltage. It started off with things like current collapse and dynamic on resistance. We'll talk about all that stuff. So once again, I go to this cross section. So you can see the source, the gate, and the drain. And you'll notice they're back-to-back gates. So on the far left, we don't show it in this picture, there would be another drain. And then it would be a repetitive pattern in that dimension. Okay, so this is the area that I'm circling right now where we're going to apply stress. It creates an electric field. This electric field generates hot carriers. It occurs high electric field, but not necessarily high current. The current could vary. If the device is turned off, the only electrons you have are those from a leakage current. If the device is turned on, you have a flood of electrons going from the source to the drain that are extremely accelerated by the electric field in there. So we'll model all of that. But first of all, let's look at the phenomenon that is the intrinsic failure mechanism. Now, why do I say that? So I'm showing on the left-hand side actual data on resistance versus time on the horizontal axis, it's log time, for a 100-volt device stressed at 120 volts at 150 degrees C. And you'll notice that the on resistance starts increasing. The actual data points are down at the bottom, and then the blue dotted line is the extrapolation of those data points. And where it crosses the maximum on resistance of the data sheet, you'll see there up at the top, that would be what we would call a failure. In other words, if something exceeds data sheet limits, we call it a failure. So all that being said, here you go. But are all devices the same? And for that, you take a look at the right, and you'll see there are actually different slopes, slightly different slopes for different devices. So in other words, in order to understand this, you have to be able to look at larger populations of devices. The other question that I get asked is, well, is this extrapolation method of using short times and projecting out, in this case, the right-hand side as many years, is that valid? And we're using the equation down at the bottom to do it. Log time, you'll see, in the bottom, that it basically says that these things should behave like the log of time. All right, we'll keep that in mind because we'll come back to that thought in a minute to prove that this is a valid way of looking at things. So the first thing we did was let's estimate our errors by using short times to project performance after long times. And if our understanding of physics is correct, log time should be a straight line. Okay, well, so what we did here is these are just two different devices. We've done lots and lots of them. And in this case, we did, it's 1,000 hours at the far end of the data taking. And then we extrapolated it out from there to 15 years. And we looked at two extrapolations. The dotted line is the extrapolation that we made after 5 hours. So just 5 hours. We took the data after 5 hours, we extrapolated out to 15 years. And then the straight line, the solid line, is after 1,000 hours. What's the error factor? On the left-hand side, it's about 5-6%. On the right-hand side, it's about 8 or so percent. So we're within plus minus 10% of projecting to 15 years if we just use 5 hours. We looked at the sources of errors. The typical source of error within 5 hours is minor fluctuations in room temperature. And so we've taken to using 48-hour data, which averages those things out quite well, so that we get about maybe a plus or minus 5% error at the end. That's our estimate today. So that's how good it is to use short-term data to project out to long-term. Now, what about the mechanism? Well, the mechanism, as I mentioned before, is hot carriers. They get really hot, and when they get hot, they can hit a lattice defect and get ejected into a trap. The trap typically lives above the barrier in the silicon nitride again. Now, what we've done here is we've developed a technology to image the trapping in real time. What happens is, as the electron jumps over the barrier, it gets trapped in the silicon nitride, and a photon gets emitted out. That photon typically is between 1 and 2 microns in wavelength. So we use a 1 to 2 micron filter in our very, very sensitive camera, and you can see the individual trapped electrons happening. And here it is on one of our devices. This is a 4th generation device. And we took this picture several years ago. Zooming in, we can see it even closer. And in this case, we've overlaid it with that purple crosshatch thing. That's actually our mask design. And lo and behold, the majority of these trapped electrons are right along the edge of the drain field plate. And that is exactly where we have the peak electric fields in this design. So, good news, things are starting to look like they make sense a bit. We get trapped electrons where we have highest electric fields. Matter of fact, we can turn the dial up and down, and we can exactly tell when the trapping occurs. I mean, it's an exponential, so you can plot it over the voltage, and we can then put quantitative numbers onto our very detailed 2- and 3-dimensional models of electric field on our devices. And that's very important because we use those to improve our devices over time. So here you go. We developed this technique, and now let's go into the theory. So what I'm showing is a cross-section of device, and I'm not even showing the source and the gate in this one, because as I mentioned, all the trapping is occurring near the drain field plate. So here's the gallium nitride, above it the aluminum gallium nitride. The 2-dimensional gas allows electrons to go from the left to the right. And there's a dielectric above the aluminum gallium nitride and a drain metal. And the drain metal is a small overlap field plate. So what happens is the electrons come zooming along, quantum mechanically compressed in the huge speed, and they hit something. And there's a scattering event. And when that happens, the electron can jump that barrier like it did in the gate, and it gets trapped in the dielectric, in this case, silicon nitride. Now, only a few get trapped. So there's a probability of trapping, and most of them go to the drain metal, and that's how you complete the circuit in the device. So let's model this. So this is showing you the band diagram. On the left is the silicon nitride, and on the right is the gallium nitride, and in the middle is the aluminum gallium nitride. And you'll notice in this band diagram, the aluminum gallium nitride, where it hits the gallium nitride, it dips down. That's caused by the piezoelectric effect. The strain field dips down, and all the electrons fall into that little dip, which actually is a huge electric field. That little dip generates huge electric field. So you see those little billiard balls kind of stacked up there in that 2-dimensional electron gas. Now on the right, we've drawn a very crude diagram of the population of electrons versus electric field. That's that blue diagram. And this is the lucky electron theory. That's not a colloquial name. That's actually a name given in physics, where you have a distribution of electrons. Some of them will have more energy than others. And as it depicts there's kind of a population, and you get higher energy, you get fewer and fewer electrons. But some of them have enough energy to get to that red horizontal line, which is the barrier height. If there's one of them that has that energy, it will jump that barrier and it will get trapped in the silicon nitride. So the game is to calculate how many of those have that much energy and can jump over that. Now, as those electrons jump over, which you can see here, we have now, instead of one, we have three. But as they jump over, they actually generate a higher barrier in the silicon nitride. That charge increases the barrier height, which you see here. Good news, because that actually that means that as time goes on, as you trap electrons, it becomes harder and harder to trap electrons. And that will come out to be that log time coefficient that I mentioned to you before. And it's I'll say, physical justification for why log time and extrapolations in log time is the appropriate way to do that. So let's now go to the math. Here we start calculating delta R over R, which is normalized increase in on resistance. And here again, we're using a hot carrier trapping model with some simplifications, which we remove later on, by the way. And it comes out to a relatively manageable equation. And this is it. And it only uses parameters that come out of literature. The only parameters that come from our device come from our calculation of electric field, quantified calculation of electric field in our 2- and 3-dimensional electric field models, which, as I said, we calibrated with the electrons being trapped. So we have a quantified model, and then we can use that electric field modeling along with physics literature on how frequently things get trapped and how they get trapped versus temperature and all that to come out with the equation above. There was one simplifying assumption in this one, and that is that the number of trapped electrons is small compared to the number of electrons in the 2-dimensional electron gas. Now, we will remove that restriction in a few minutes, but in the meantime, it makes for a very easy calculation. Also, notice there's the log time coefficient, which gives us, I'll say, good confidence that using extrapolations with a log time is a valid extrapolation. So let's see how it does. So on the left-hand side, we have actual measured data. The solid lines on the left are extrapolations of that data, as I showed you before, plus or minus a few percent. These are 48-hour measurements, and on the top, they're measured at different voltages, 60, 80, 100 volts, and 120 volts. These are 100-volt devices, and these are in our generation 5. We're now half a generation beyond that, and generation 6 will be coming out in a few months. But it was generation 5 that we designed to have virtually no dynamic on resistance, and that's really true. So you can see there, even at 120 volts, these devices have moderate dynamic on resistance after 10 years, but within the data sheet of 100 volts, really it's less than 20% after 10 years. Now, if you look below, you'll see again this counterintuitive thing where at higher temperatures, you have less dynamic on resistance. So all those people out there that love to do qualifications at high temperature and high voltage, realize you're making it easy on us GaN folks. That doesn't necessarily stress the device as much as at lower temperatures. So at higher temperatures, less and less dynamic on resistance. On the right, you'll see the model data. It very closely matches the measured data. Now, some of the consequences of the model are that it says there should be very little dependence on current. And here we've taken a device, and it's normalized on resistance on the vertical axis, log time on the horizontal axis, and we took it out at 12.8 amps, then 25.6, and you can see they're both on the same slope. So there's really no impact to first order of current. And in our very detailed calculations, we have a coefficient for current, but it's very small. How about switching loci or inductive versus resistive switching? The path that the electrons take in an inductive switching cycle are very different than the path they take in a resistive cycle. Makes no difference, none whatsoever. Now, some people think of inductive switching as soft switching. Soft switching is a form of inductive switching, but it's not the same thing. This is hard switching inductively. But if you do soft switching, you don't get any dynamic on resistance because there's no electric field during the flood of electrons. So it's virtually zero. So doesn't matter if you're doing inductive or resistive, and it doesn't matter how much current you pump through these things, but it does matter how much voltage, and it does matter how much temperature you have on these things. Those are the key variables. Now, I told you about a simplifying assumption that the trapped electrons were small in quantity compared to the two-dimensional electron gas. We remove that restriction, and what it means is you have to numerically crunch some fairly complex integrals, and we've done that. So here you see the no assumptions or simplifications calculations. In this case, the model are the straight lines and the dots are the measured components. This is the same vintage device that I showed you in the prior one. It's a 100 volt generation 5 device. Again, 80, 60, 60, 80, 100 volts, 120 volts, and then 150 volts. And you can see there's a curvature that's developing. And that curvature comes from the fact that when you have a small number of electrons less, your conductivity gets higher very quickly, or your conductivity gets worse very quickly. It's a consequence, for example, that resistance is 1 over conductivity. And on the right, you see it versus temperature. Again, higher temperature, less effect. So these devices not only will withstand huge amounts of overvoltage, but see how they fail. It's very soft fail. And that's a big difference between silicon and gallium nitride. These devices are incredibly robust. And if for whatever reason you overvoltage it, it tends to take a ding out of your on resistance as opposed to an explosion on your PC board. We've done the same thing at 200 volts. We have the models at 40, 200, 100, all the models, again, using physical parameters, augmented by our detailed modeling of the three-dimensional electric fields in our device. And they all behave, I'll say, perfectly predictable in that way. Now let's move to current stress. And we're going to look at current stress first by safe operating area. Safe operating area is where you put an amount of current, and you also apply voltage to the device while you have that current. And in so doing, you can create an area of operation, whether or not that you can use it. And those tend to be limited by thermal heating of the device or the system. So here's an example of a safe operating area of a 40-volt device. Vertical axis drain current, horizontal axis is drain source voltage. The solid black lines that form almost a square, that is the highest, that goes at 40 volts, and it goes up to the pulsed current rating. So that would be the combination of voltage rating and pulse current rating. However, the lateral, sloped lines on the right, there's a green one and there's a purple one. Those are constant power lines at different pulse widths. So, for example, the purple one is at a millisecond, and the green one is 100 microseconds. And then all the green dots are where the 100 microsecond pulses were done, and all the red, the purple triangles are where all the millisecond pulses were done. We show them all here, and you'll see the red triangles are where things failed. They all failed above the thermal limit for the device. Same thing at 100 volts, and same thing at 200 volts. So in all cases, we've done failures on these things under the entire safe operating area that's on our data sheet, and they will successfully meet that. Now, why is that important? First of all, notice that the power limit, that lateral line on the right of each graph, purple and green, those things are straight lines. That's a constant power. Now, in a MOSFET, you do not have a straight line, and that's because of something called the Spirito effect. It's a secondary breakdown effect in MOSFETs, and it gets worse and worse as the MOSFETs get better and better in terms of figures of merit on resistance for a given die size. So it limits your ability to use these MOSFETs and their delicacy under certain overload conditions. But you don't have that in GaN. GaN is very robust. It is a wide bandgap semiconductor, and they are hard to break. And I'll show you how hard to break they are by looking at short circuit, something that typically MOSFETs aren't subjected to. IGBTs, yes, but not MOSFET. But we're going to do it. We're going to blow up devices under short circuit. How much of this can they take? So let's look at it. EPC 2203, it's AEC qualified generation 4 part. Also look at a later generation, and there it is. It's 0.8 by 0.8 millimeters, so it is tiny. We'll also look at a Gen 5 device, the EPC 2051. It's just a little bit bigger. It's 0.9 millimeters by 1.5 millimeters. Again, tiny devices. These are really, really small. People would look at them and just, can't get anything through that. Okay, well, here's a table. Now, in this table, we really abuse these devices. First of all, how to read the table. On the left-hand side, you have a bunch of characteristics, which we'll look at, but then you have the Generation 4 device in the middle columns and the Generation 5 on the right hand. But what we did was we tested them with unlimited current with the gate source voltage at 5 volts, which is our recommended drive voltage for everybody, and then 6 volts, which is the maximum you can put on that gate. So you're really opening the valve to the maximum and letting everything through at 6 volts. That's as much as you can get. And we did the same thing on the Generation 5 device. So the die area of these things, as I said, is tiny. The one on the left is a little less than a square millimeter. The one on the right, just a little bit more than a square millimeter. And the average pulse power under these conditions was, in the case of the Generation 4 device, at 6 volts. In other words, valve wide open, 1.8 kilowatts went through that device. And in the case of the Gen 5 device, 3 kilowatts went through that device. 3 kilowatts, so this tiny little piece of semiconductor. And what happened? Well, the minimum time to failure, not the mean, the minimum time of failure, you can see here. The Generation 4 devices failed with the valve wide open at 12 microseconds, and the Gen 5 device at 9 microseconds. Now, these devices have full control right up to the point of failure. So they don't lose control before they fail. They fail with full control. So if you have a short circuit possibility in your system, you have plenty of time to shut the thing down before these devices will fail. Okay, so next, we're going to look at a real-world case, a synchronous rectifier with a bad design. And here's the example. This is a synchronous rectifier. It's a circuit that we actually have in some of our demo boards, and the output of, for example, our kilowatt demo boards use this configuration. And you can see there are a couple of devices. There is a device. They're both, in this case, I showed 30-volt devices, and we'll talk about 30-volt devices. There are 2 of them in this circuit, and that is parasitic inductance. So we're modeling parasitic inductance, and that's what we will change. If you have a good layout, you don't have much parasitic inductance. And again, this is parasitic inductance in addition to the transformer inductance, which you can see right above it. So what's the impact of that? Well, with 50 picohenries of parasitic inductance, this is the waveform you get. Okay, nice clean waveform, a little bit of overshoot. Again, these are 30-volt devices, so the top of the scale here is 30 volts. And we'll call this case 1, good design. The red or orange is the drain current, which you can see, and then the drain source voltage. Okay, let's do a bad design. In this case, 150 picohenries, which that's a few millimeters of stray copper actually that'll do that. So you have to be careful. 150 is not great, and you'll notice that at 150 we actually get spikes that in the real world they go up about 35 volts, and this is a 30-volt device. Is that problematic? Well, it's not recommended. We recommend good layouts because they have less ringing, and that also leads to lower EMI. But what about this? How is it going to work? So we did real-world modeling. We took away all the simplifying assumptions, and we actually crunched the integrals, which takes a lot of computing power, and we crunch them in a 50 picosecond grid out to 10 years. This is what you get. In the well-designed case, on the left, we show actually the number of trapped electrons. Okay, so in this case, it's how many electrons per centimeter squared times 10 to the minus 12. Okay, and there's your answer. Not many. And on the right-hand side, we show its impact on resistance, and you can't measure it. So again, this stayed below the maximum limit of the device. Great. Now, here you go in the case of trapped surface charge in the badly designed case. So we're going over the theoretical limit, not the datasheet limit of the device, and you can see there's some trapping occurring. This is out 10 years, but whoa, what about those traps? And the impact of on resistance, as you can see here, is a few percentage points. It's not catastrophic. It's just a few percentage points. Matter of fact, it comes out to be up 5% in this case. So you can really take a real world condition and you can see, what are the impacts of my ringing or overshoot or those things using our physics-based models. So let me just summarize it and take your questions. Number one, GaN device failure mechanisms are not very temperature sensitive. Okay, GaN is a wideband gap semiconductor, and much like silicon carbide, not very sensitive to acceleration from temperature, more sensitive to acceleration from trapping, which is voltage and temperature sensitive. Voltage and has a negative temperature coefficient. So hot carrier trapping and the impact ionization are two key factors that cause long-term wear out. It's way long-term. It's longer than any of our products will last. And real-world circuits show that GaN can withstand very large overloads in voltage and current without catastrophic failure. And really, I think that there's so many different examples of this, not just from us, but from academia, from the rest of the world. The only people that are saying otherwise now are just the silicon MOSFET people who are, magical thinking that GaN has problems. And so GaN is more rugged, and it is more reliable than silicon. And in the end, in the world of power, it's a better power semiconductor. And with that, let me take your questions.
Okay. So thank you, Alex. We are going to start answering the questions that were submitted during the presentation. And just as a reminder, you can still submit questions using the Q&A feature at the bottom of your screen. So feel free to continue to send them in while we go through the ones that came in already. So first question, Alex, is does the GaN FET, such as the EPC 2218, fail short or fail open at overcurrent conditions?
I think that if you're really overcurrenting, which takes a lot, I mean, that's hundreds and hundreds of amperes, it will tend to short. Most power devices tend to short, and I think this is no exception. Yeah.
Okay, and what about over voltage and over temperature conditions?
Well, in over voltage conditions, I think I showed you, it's soft fails. The on resistance goes up and up and up, and if your circuit continues to pump enough current into it as the on resistance goes up, the power dissipate in the device will get too high, and then it will once again fail, but it will fail in a short circuit.
Okay. You had a slide showing the impact of ionization. What's the impact on space for satellites since ion and charges are a concern?
So impact ionization is a phenomenon inside the device from hot electrons. It's a very good question about radiation. And for that, we did, in fact, in our test to fail methodology, we fully characterized these in radiation. We did a conference a couple weeks ago, NESREC, where we showed our newest generation of devices specifically designed for radiation, our EPC 7000 series, and what we say is they're immune to radiation at this point. You can't fail them with gamma radiation because there's no failure mechanism. In a MOSFET, the failure mechanism is trapping in the gate oxide. In our devices, there's no failure mechanism. So put 100 megarads on them, they don't fail. They don't even change. Then you can go to neutrons and protons, which have mass. And so the mass going into the crystal can create displacement damage. In other words, it cracks the crystal eventually, right? But GaN devices have a much tighter bond between the gallium and the nitrogen than silicon does. So we have multiple orders of magnitude less displacement damage for the same amount of neutron or proton bombardment. So they're virtually immune to proton and neutron bombardment. We've taken them out to 1 times 10 to the 17th dosages now and seen very, very minor, just the beginnings of displacement damage. And that's more than 2 orders of magnitude over where a silicon device will fail. And then there's single event. That's where you take heavy ions and you blast them into the device. And that's particularly pernicious because single event in a silicon device can do several things. One is it can rupture the gate. That's called single event gate rupture, or SEGR. When that happens, the device is bad. Second thing it can do in a silicon device is it can create a huge whole electron cloud, and that's single event upset. That's pernicious because it's a short circuit for a very short period of time. And because of that, you can get shoot through in half-bridge type circuits. And that's the reason why, since day one with MOSFETs, power supply designers for satellites have been using like single-ended flyback topologies for DC to DC converters, even though it's much less efficient than a half-bridge. But in a single-ended flyback, if it short circuits the device momentarily, it will not kill the circuit. In a half bridge, if you get a short circuit, you get shoot through and it'll burn up. GaN does not have any of those failure mechanisms. So GaN devices withstand all that stuff, and you can now safely go to the most advanced, efficient topologies in the commercial world with your radiation designs. Now, GaN devices eventually will fail under single event, but it's above the 85 linear energy transfer units, which is megavolts centimeters squared per EV, I think. And it's above the limit. That's as far as the dial will turn on these accelerators. And all our devices go at maximum LETs. And the failure mechanism there is displacement damage, heavy ions creating displacement damage, but well beyond the limits. So we can safely say, forget about radiation when you're using GaN. Worry about your silicon devices. They're delicate.
Great. So the charts show at 1 ppm, the gate voltage is 6 volts. Is this the maximum voltage that we should use?
Yes. We model this thing and we fail millions of parts. There's no reason to go beyond 6 volts. 6 volts is well beyond the full enhancement of the device under any moderate condition or even non-moderate condition. So if you stay below 6 volts, you'll never have to worry about a gate ever in your lifetime or the lifetime of any of your grandkids or great-grandkids. Over time we may decide to increase that, but it needs to be based on a body of a huge amount of data at this point. So in each new generation, we look at those things and we evaluate it. But right now, stay below 6 volts, you'll get below 1 ppm failure rate.
A typical silicon MOSFET with overvoltage goes into avalanche condition. That does not happen in GaN. So does a 100-volt device hold up to 150 volts?
Yeah, I showed you data on that. It does hold up to 150 volts. We over-test every single device quite a bit. Unlike MOSFETs, these devices will withstand lots of overvoltage, and they soft fail, they don't hard fail. In other words, the on resistance just kicks in. Now, in our devices, we have a 20% overvoltage on the data sheet. So that amount is okay in a transient. More than that, you're still not going to see a failure in these devices. It's just not recommended because it starts degrading faster.
Okay, I'm going to ask your favorite question. Is a negative gate bias ever needed?
No. No. Stay away from negative gate biases. That just, there are a lot of people. No, so I get that question. I love it. So there are people throwing out there willy nilly that you need to turn these devices off with a negative gate bias. And that's for two reasons that myth has gotten out there. One is that there are gate injection transistor devices, first developed by Panasonic, now sold by Infineon. And they are gate injection transistors. They are not field effect devices. They need a negative gate voltage to pull the charge out of the gate. They need positive and negative, bipolar gate drive. No question about that. We don't make those devices. Don't do it with us. Second reason that is the myth that the device will self-trigger in high DVDT and you need to hold it off. Well, the reason people have that myth is for two reasons. One is badly designed GaN devices, and the second one is GaN devices where the threshold voltage shifts down to below zero because they're not reliable. Both of those have been out there in the past, but really aren't out there anymore. But there's a thing called a Miller ratio, and that's the ratio of the gate drain charge to the gate source charge. And if the Miller ratio is below 1, it's all written up in our book. If it's below 1, you cannot false trigger it from any amount of DVDT on the drain source side. It will not false trigger. All our devices have a Miller ratio below 1 from 0 to full rated voltage, so you cannot false trigger them. All our devices have a positive threshold voltage under all conditions for their entire lifetime. So you cannot false trigger them ever. Don't use a negative gate voltage. Now, what's the harm in a negative gate voltage? Is if you use these devices in the third quadrant, in other words, reverse conduction like a diode in a MOSFET, the negative gate voltage actually raises the forward drop of that simulated diode in the reverse direction. So you will get higher losses if you have any third quadrant conduction. So don't do it. It's not needed. It usually adds cost and it degrades performance.
Great. Can you also comment on the reliability of GaN ICs, for example, the EPC 23101? What is the status on the stress testing there?
Yeah, we'll have a bunch of stress test results out in our phase 15 report coming out in December. We have qualification data that we put up on the website as these devices qualify. I think the 21601 is up there now, fully qualified IC. These devices they're qualifying very well. They're very, very reliable devices. Obviously, with ICs, you have to test them a little differently. So we do a lot more high temperature operating life conditions and low temperature operating life, stress them in every different way. Our knowledge of the intrinsic failure mechanisms for discrete devices is very important in our design of very reliable ICs. So if you call in or write, ask a GaN expert, we can give you whatever data is available at that time. In the meantime, in the phase 15 drop, there'll be a lot of data there.
Okay.
No surprises, by the way. There are just no surprises.
Okay. The 650 volt device from GaN Systems recommends negative gate voltage. Is there a difference for the gate voltage between lower VDS GaN FETs and higher VDS GaN FETs?
It's just whether or not they design their Miller ratio well. So their Miller ratio goes above 1 at 600 at higher voltages. So they recommend that you put that negative bias on there if you're using it at the higher voltages.
Okay.
Not true for any of our devices. None. They've all been designed very carefully, Miller ratio less than 1 under all operating conditions.
Okay. How do GaN devices behave in X-ray applications compared to silicon devices and silicon carbide devices?
We've done extensive X-ray. Most of it's classified. What I can say is they behave like you would expect GaN to behave. Just shrugs it off.
Okay. What techniques did you use to show that holes are trapped in Si3N4 in the very first example, dielectric rupture for impact ionization? Your phase 14 report says there's convincing evidence, but doesn't say anything further.
Yeah, so you can basically find out if holes are coming through your gate, and I think there's a pretty good description of that in our Phase 14 report in the appendix. If not, if you just send in and ask a GaN expert, we'll get a more complete answer. But we did a bunch of tests to see, is this holes, is this electrons, is it something else, whatever, and we did all that stuff before we could come up with a theory that fit all the data.
Can GaN devices support more than 100 volts? For AC/DC power supplies, we are looking for the spikes more than 500 volts.
Well, I don't think a 100-volt device will take a spike up to 500 volts. You can, if you want to do an AC input, you can get 650 volts from lots of GaN producers. They're very excellent ones out there. Navitas GaN system, to give you two. And if you want to do it with lower voltage devices, take our 200-volt devices and use a multi-level. Works very well, by the way. And depending on how you design the multi-level, you can add up the overvoltage capability of our devices to decide on what's the overvoltage capability of the multi-level system. There's some interesting work by Alex Wang at University of Texas, Austin. We've done our own work. University in Bern has done work, and they all point to one thing, and that is that the power densities achievable with multi-level converters is higher than the power density achievable with two-level converters. That would be like a half bridge. In the case of an AC waveform, AC input, that would be 600-volt devices in a half bridge versus 200 volts in a multi-level converter. You'll get actually higher power density with the lower voltage devices.
Is there room to optimize the GaN device switching time?
Sure. Yeah, I mean, it depends on what's causing limitation. We found that the limitation, again, switching time is typically limited by the layout, the quality of the layout. And why do we know that? Well, even in our own guidance on layout, we have an optimal layout. You can see in our book, you can see our data on our website, and it's very important, by the way, to look at that because it really is a very clever, very, very efficient layout. But even with that, there's some picohenries of parasitic inductance, which can slow a device down. If you buy our integrated devices, for example, the driver integrated with the power FET, you will get an even faster device because we've eliminated some of the key parasitic inductances that slow the device down. They tend to be the limitation. Common source inductance, number one, power loop inductance, number two, and gate loop inductance, number three. Those are the three parasitic elements that slow a device down. Our FETs plus driver series have no common source inductance and no gate loop inductance. Our power stages, monolithic power stages, have no common source inductance, no gate loop inductance, and the power loop inductance between FETs is also gone because the FETs are integrated together. So all you have is the power loop inductance that comes from the loop that includes your capacitors.
Can a GaN FET survive gate voltage spikes greater than 6 volts?
Yes. Yeah, and I think that we showed the evidence of that on these graphs. It's not recommended. Don't like to see people doing that because sometimes these spikes are so high they don't, it's hard to see exactly how high they go. So stay below 6 volts, but you can see here we've tested them out to 10 volts. And if you want a very short lifespan, take them out to 10 volts. And what is that? That's probably a few minutes of life. But again, close to 6 volts, you get almost the age of the universe in terms of lifetime.
Okay. If your RON increases due to a parameter like temperature stress over voltage, does it return to the initial value again in the absence of that parameter?
Okay, I think my understanding of the question is if the on resistance increases, dynamic on resistance increases because of high voltage applied, with or without temperature. Less temperature, it's actually more of a problem. Does that recover? Does the dynamic on resistance recover? And the answer is it's a fake if it does. GaN is wily about that stuff. What happens is that when you remove the voltage from the device, you will see the on resistance go back close to its original state if you stressed it to where you have dynamic on resistance. So now it's gone close to the resistance. You get all excited and say, wow, it fully recovered. But what happened is you just attracted mirror charges that basically mask the trapped charges in the silicon nitride. And the minute you turn the device on, those mirror charges go away. You have the dynamic on resistance. So they go away within seconds. So you tend to get a false sense of recovery in this thing.
Okay. We have two more if you have time, Alex. Is it okay?
Yeah.
How can you improve the time of short circuit failure mode?
Well, there are various ways. Let me go back to that one. So if you really need them to stay in a short circuit condition for longer, you can buy different devices. But let me go up here on the. Oops, sorry. Why is that not cycling? Hang on a second. Okay, so there's the minimum time to fail. It's above 10 microseconds. But you'll see that at a gate source voltage of 5 volts, the recommended voltage to drive these devices, it's really about 20 microseconds. And that's plenty of time usually for a circuit to limit itself. If you need it to last longer than that, first of all, you got to ask yourself, why is that? But then you got to go back to the SOA curves that we showed earlier, and you can see how long they'll last at different pulse widths. So these SOA curves are really survival curves, but you can also see the red dots here that tell you the failure time at the various conditions. So on the one on the left at 40 volts, you can see that. Let's see if I can circle this here a little bit. Let's see. So let's look at this dot right there. That dot is at about 20 volts, and it's about maybe an order of magnitude over the power limit. Maybe factor 6 over the power limit. So it's running a couple of kilowatts at that point. But take a step down from that, and it's lasting a millisecond. So if you have a short circuit condition that's lasting a millisecond, run these things at less than 20 volts, and they will never fail.
Okay. So I think this question is, how do we know that we've never had a gate failure? Because I guess we're assuming somebody would have to claim that they've seen a gate failure for us to know that there's been a gate failure, right?
No, not necessarily. First of all, as I said, we get every failure back if it goes in a car or a telecom base station type equipment. They're they have all sorts of ways of figuring out that you have a failure. When you have a failure, they will tend to not only let you know, but they'll give you an opportunity to find out why it failed. And in particular, they will give you an opportunity of doing it under intense pressure while they look over your shoulder with lots of people and lots of conference calls. So what we need to do, and did on those 3 that we had back there, is you tear them apart, you do very careful failure analysis, and then you can tell sometimes what the cause of failure. In the case of these, we were able to. So that's how we know. I mean, they're just still running in those applications after 400 plus billions of hours. So no gates. Those 3 failures were not gate failures. They actually were drain source failures.
Okay. And finally, when the RON shifts first temperature, is it the junction temperature or the ambient temperature?
Well, the RON shift is a function of the temperature where the hot carriers are being generated. And the reason for it going down with temperature, let's see, there's a good example, goes down in temperature, is that as you go up in temperature in the 2-dimensional electron gas, so right there at the junction, the mean free path of electrons goes down, because what happens is the lattice starts vibrating, it creates phonons. These electrons can get hit phonons, and when they hit the phonon, they lose energy. They transfer it to the phonon. And so your hot carriers are less likely to have the energy to jump over the barrier. And that's why in both the impact ionization and in the dynamic on resistance, the hot carrier mean free path going down with temperature is the primary mechanism for improved performance at high temperature.
Okay. All right. Well, thank you, Alex, very much. And thank you, everyone, for attending our webinar. If you have any additional questions, please send them into info@epc-co.com or visit the GaN Talk support forum, where you can have access to product and design support and also share ideas on the use of GaN-based power technology. You will receive a follow-up email within 24 to 48 hours with a link to view a recording of the webinar. And lastly, please be sure to register to attend the remaining installments of the Summer of GaN webinar series. Our next one is on August 17th, where Marco Palma will discuss how to design smaller, lighter, and more efficient motor drives. Visit our website at epc-co.com for more information and to register. Thank you for joining us today, and have a great rest of your day. Thanks again, Alex.
Thank you.
Thanks. Bye.